No.
I can.
You guys
It says I can take control of the presentation.
You can, if you don't, but you can. Okay, there's a crappy movie called Torque. Yes, Rosie? Okay, any of these that are particularly helpful? All right, so you need some sort of pivot point. That makes sense?
Yeah.
Okay, so this is the top-down view. You guys looking at the PowerPoint?
Yeah.
This is the top-down view.
Which one are you at? Which one are you at?
Slide 11?
Okay, I'm here.
All right. So if you think about just opening a door, if you try to push it at the hinge, what happens?
It's harder to push.
Yeah.
If you're right at the hinge, what happens?
It doesn't.
Nothing.
Nothing, exactly. So you could have a force and yet no rotate. So if this door, how do I put this? You could think of, you know what, let me actually, I'm not going to share this. Let me just draw some stuff. I'm going to share my screen. All right. This might be a good explanation here. Okay, you guys see this?
Yeah.
So if you just have some square and it's free to float around, and you push it with these forces, this is actually a question that's on one of the reviews. They're the same, whatever. They're 5 newtons. One's up, one's down. What's the net force on this thing?
0.
0. So the whole thing is not going to accelerate anywhere. However, look what's going to happen. Like if the center of mass is here, what would happen to this thing?
It's going to start spinning.
Yeah, so the net torque is not 0. So torque is a turning force. It means that in this case, the idea is you take, to solve these kind of things, the point of application of the force, like right here, and you draw the lever arm, which is to the pivot. Now, in this case, okay, what would happen? Okay, so the pivot is here. What would happen? And let's say it's pinned to the ground or something. What would this force do? Would that force? Yes, Rosie, we're paying attention to you. Would this force turn it at all?
No.
No, exactly. So what's the difference? Why would this force not turn it, but this one does?
Because it is, I don't know how to say it, but it's in line with it's in line with like the radius. Like if you could draw.
That is exactly right. That is exactly right. It's like if you had a door, this is a top-down view of a door, and you pulled this way, nothing would happen, right?
Yeah.
That makes sense?
Yeah.
Okay, so torque means you have a force that's not only some distance from the pivot, but it has to have some component that's perpendicular to that pivot, which is why the equation is FR sine theta, because if you're not perpendicular, this is 0.
Right.
So you have to be both a distance from the pivot and perpendicular, some component perpendicular. This one here that we did before, this is not completely perpendicular, right?
Right.
But it's got a component there that is perpendicular. So this part of it is the part that's perpendicular, that's doing the turning.
But isn't the pivot like the line that you drew? Isn't that just arbitrary?
Arbitrary, not exactly, because, well, if it's a door, the pivot's in its definite place, right?
Right.
So that R is not arbitrary. It's the distance from the point of the force to the pivot. It turns out if you just have some free-floating object, the pivot is the center of mass. You could try by like taking a pencil or something and flipping it in the air. You'll see it'll always rotate around the center of mass.
Right. Okay, so it can't be in line with a radius.
Exactly,
It's
because
in
then
the block.
then sine of 0 would be 0.
Right.
And you're not turning it anywhere. Yeah.
Okay.
So that's the idea about torque. I think that latter problem, if you go to the one I was doing with Marco, did you see any of that we were posting?
I started looking at it and I glanced at it, the problem, and I wasn't really sure what was going on.
Yeah, that's fine, because glancing at it, that's like the toughest possible one. So I have a video discussing it, and let me just tell you the basic principle.
What's the next slide in the PowerPoint? There was one that had like IA, and I didn't know.
Oh, let me tell you about that. Yeah. Okay, so that's your analogy to net F equals ma. Rosie's trying to hit the keyboard with her foot. So you got net F equals ma, right?
Right.
But if you're turning, it's just an analogy, I alpha. So this is rotational mass, and this is rotational acceleration. We already did alpha.
Right.
I, the fancy name for I is moment of inertia. If you're an engineer, you'll talk about that a lot. It really just means rotational inertia.
What is that?
What is it?
Yeah.
Let me show you. At that point, the PowerPoint slides actually might help a lot. So,
Because when I looked at the slides, I
Let me
didn't see
get
anything explaining I.
there is. It's near the end.
Oh.
I don't think you're recording, Mr. Greenspan.
I am now, yeah. All
It
right.
says recording is about to start.
That's weird. It says I'm recording.
That's
Okay.
just you.
I'm just. All right.
Okay. All right, let me share the PowerPoint again. All right, you guys see the PowerPoint?
Yes.
All right, so it's actually near the end. So on the new thing I loaded, I have, for each part, I have like slides. Here's moment of inertia, I. So it's rotational inertia. These are actually viruses, which is pretty, or bacteria, so it's kind of appropriate for what we're going through right now. They each have different moments of inertia. If you notice their units, piconewtons times nanometers. So that's a torque unit. How much torque? Because like these bacteria like drill into your cells. It's kind of gross when they kill you. All right. So you see this slide with the rotational inertias?
Yes.
All right. So inertia is mass. Mass and inertia are kind of the same thing. They're how difficult it is to accelerate an object, right?
Sure.
Rotational mass would be how difficult it is to angularly accelerate an object.
Okay.
All right. So if something had 1 billion kilograms of mass, but no volume, no radius, it still has that mass, but it wouldn't have any rotational inertia because it wouldn't be able to turn it.
Sure.
So look at these two, the rods. Do you see my arrowhead?
No.
Okay, I'm trying to like, what would I point with? But the thin rod about the center, and then below that is thin rod about the end?
Yeah.
Which one is harder to turn?
The one about the center.
No.
The bottom one?
Yeah. Think about that. Like try to turn get something like heavy or like something that's really long and try to like spin it around the center and then try to spin it around just holding the end.
But
the radius is way longer, so it's harder to spin.
Right, but you can exert less force, right?
Okay,
Because...
so this is assuming the same force.
Oh.
Just like it is with F equals ma. If you want to know about the mass, you got to assume the same force and then see what the acceleration is.
Right.
Yeah, you're thinking about like biomechanics and if your arm is swinging or something. But you assume it's the same torque.
So I was thinking like the door analogy, like, you know,
Yeah,
it's
that's weird.
your,
So that's the torque. You have to, yeah. So in that case, you're exerting more torque, but like the rotational inertia of the door isn't changing.
right.
But if you try to open a door that's okay. Rosie's not happy. Bugs. Hold on, guys. We get to hear. Oh, Rosie, see? You want to see the PowerPoint? Learn some physics? Oh, Rosie. Up, 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 up. Ba-ba. Ba-ba. Oh, ba-ba. Oh. I'll go down. Yeah. Okay. All right, guys, hold on a sec. Oh. Hey, you want? Oh, whoa. Love bug. Dylan,
Yes.
think about if you had the same door. This is a little. I don't know if this analogy is good, but if it's the same door, like the same. Sorry, not the same door. Two different doors, the same mass, but one has less length than the other one. It's like easier to open because it's shorter.
Right.
That's the idea. Or you think about the these two flat plates at the end here. Which one of those is easier to turn?
Probably the flat about the central axis.
The bottom one, right? Yeah, exactly. Because the radius is smaller. That's the idea. So that's rotational inertia. You can see the actual equations here. Hold on.
It generates more torque than there's.
It's not generating torque. Think about mass. The mass has nothing to do with whether you're exerting a force on it. The analogy to mass is very strong. It's just
So
how
it's really just about the radius.
and the mass, both of them. Like if something's heavier, it's also going to be harder to turn. Look at the equations here. You got 1/12 ml squared. This one is mr squared. 2/3 mr squared. So the mass matters.
Yeah.
The heavier it is, but the farther those, you know what's a good one? Look at these two. Solid sphere, go back up. Solid sphere versus hollow sphere. If they have the same mass, which is harder to turn?
If they have the same mass,
Yeah, exactly the same mass.
then it's the same.
No. One of
Whether
them is
it's
hollow.
solid or hollow.
Yeah. But one of them, but they have the same mass.
The radius is exactly the same though.
Yes, but one of them is hollow.
What
One of
difference does
them
it make if it's still the same mass?
The solid one, the mass is distributed throughout the whole thing, and the hollow one, all the mass is on the outside.
Oh, so there's more mass on the side.
Yeah. Look at these equations. Which one is bigger?
The bottom one.
Exactly.
So,
Probably not.
So it's all about, it's not just mass and radius, it's the distribution of mass.
okay.
If you have a baton or something you're swinging, or if you have a bat, think about a bat, but you moved all of, like, it was a very, very thin bat and all of the mass was on the end. It would be harder to turn, harder to swing.
Yeah.
So that's rotational inertia.
Are we gonna
How do
have
I
to
submit
figure
the
out like
test
what
question?
that is, or just
So you don't need to know these equations. Like, so if you go to APC with calculus, you could actually derive these equations. On the AP test, it's more like if you need one of these equations, they'll give them to you.
Oh, okay. But we're not responsible for memorizing this stuff.
No, no, no. You just, on your reference table is net torque equals I alpha. Let's go back to, wait, whoops. So see this, net torque equals I alpha?
Yes.
Let's go back to my beautiful drawings. So you have your analogy here. You have net F equals MA, and you have net torque equals I alpha. This is rotational mass, pen. And this is rotational acceleration, but it works exactly the same. A lot of these problems, like with that latter problem, you got to do both. And if you're an engineer, you'll see this more too, or more higher level physics. I hope you go into. Well, what usually generally tends to happen is that like you do net F equals ma, and it turns out you have like too many variables and not enough equations, so you end up doing. Oh no, this is the eraser. You end up doing a net torque equation too to get yourself more equations. That make sense?
Yeah.
So we can do like, I'm going to start that latter one.
Sure.
So with the latter one, oh, whoops. So if you'll see this in the torque worksheet. This is an interesting part. Okay, if you have like a seesaw and it clearly has a pivot point here, right?
Mm-hmm.
And you have two people. Those are people. Then you know where the pivot is, especially if this thing is accelerating. If this thing is moving, why is it so big text? Where's the... I don't see font size. That's weird.
Just as a side thing, the person on the longer end has more rotational mass?
Correct. They do. If accelerating, you know where the pivot is. Pivot is, but if it's in equilibrium, why can't I type anymore? Choose font. What? Stop working. Vector fill. All sorts of weird stuff I gotta learn on here. If in equilibrium, you can choose your pivot, also known as the axis of rotation, same idea. It's just more dimensions. So for the latter problem, and a lot of problems like that, as long as you're not moving, you could literally choose any point in the entire thing, and that's your... Can I move this? How do I move this thing? No. I can, whoop, can do that to it. This should be easier to work with. So for the ladder problem, the ladder is not moving. Right? So you can choose, here's the ladder, here's the floor, here's the wall. You can choose what point you want to be the point of rotation, even though it's not actually rotating. But it really helps because there's still torque sort of being applied. This can actually work for any of the problems we used to do, you just didn't need them. So there was no friction with the wall, so the different forces were Fn with the floor, Fn with the wall over here, friction this way, and then there's the weight of the ladder. That makes sense?
Yeah.
There's no friction with the wall. You could make friction with the wall. In real life, there would be. That just makes it more complicated. But this is a torque diagram, not, I would call not an FBD. The regular you usually draw both. The regular FBD could just look like this. mg Fn Fn. See the difference?
Yeah.
So the FBD, you could do the net all your net F equals MAs and be fine, but you don't know any of the lever arms. You can't do torques.
All right.
Right? So, what's the static? Is that you?
I don't know.
I don't know. It might be me, but
Okay.
I don't know what. I don't think it's me.
So what generally you do is you write your net F equals MA equations and you write your net torque equations, and you have multiple equations. Do you want me to write them, or you want to look them over yourself?
Do you need both sets of equations?
In this case, yes, and a lot of these problems you do, yeah.
So how would you go about doing a problem like this?
Okay, so the net F equals MA you know how to do. The thing's not moving. Can I just zoom out here? Oh, crop and resize. Oh, here we go. Social media size? What is that? Instagram size? You could do that. That's funny. Apply crop. Whoa. Hold on. I'm playing with stuff. Size of screen. That's a little bigger. Okay. All right. So your net, let's just do a new screen. Actually, can you like take a screenshot of this so you have it?
Let's just FBD stuff.
Okay, this part too is important though.
All right.
This ladder thing. All right. So your net F equals MAs, whoops, are simple. You have net Fx equals MAX, net Fy equals MAY. So your X values were your frictional force minus the normal force from the wall. You know how that was in the X direction?
That equals 0.
Yeah. And Y direction was normal force from the floor minus mg equals 0. So all those are equal to each other.
Is it just FG or is it some component of it?
The Fn from the floor was straight up. Just because the ladder was at an angle, the normal force is still straight up.
Okay.
We're not talking about a ramp here.
Yeah.
Okay, so this isn't enough. So you do your torque equation too. It's 0 because it's not accelerating. So now the first thing you do is you figure out which point you want to make your pivot point. So what's a good one to choose?
You chose the point where it's the floor, right?
Yes, because at the pivot point, what do you know about the torques caused by those forces?
0.
Exactly. So you
can disregard friction and.
Yeah. You could choose any point. Like Marco, if you look at the video, Marco chose the middle, the weight point, the point in the middle of the ladder, and that's fine. It works out the same.
But that's more steps.
Exactly. Just another term. Not even more steps, just another term. I'm going to write all the torques out. So you have the torque from the normal force. You have the torque from friction. I'm going to make them 0 later. The torque from mg and the torque from the wall. But because of the way we chose it, these two are 0.
Right.
Now these two, you have to decide first, are they positive or negative?
Um,
The convention is that counterclockwise is positive.
counterclockwise is positive?
Yeah.
Okay. So in that case, then aren't they both? So they
Well, they
can't both.
can't be. How would it equal 0?
Right. Right.
So if you think about, we chose this as our pivot point. That's mg. That's the wall.
Oh, and that's our pivot point. Right. So
Yeah.
Yeah.
MG is MG is
Okay.
Gil, is that you?
no.
Yeah, I gotta go. I gotta go.
Okay, see you, Gil.
Bye.
Bye. All right, that's better. So which one is counterclockwise, which is clockwise?
MG is clockwise. So.
Exactly. So we'll make this negative. All right, so the torque is the force times the lever arm times sine theta. So the force is mg. The lever arm is half of the...
It was 8, so 4.
Yeah, exactly. So that's half of that. Oh, wait a minute. I feel like I... Oh, no, that's fine. All right, so that's, yeah, I'm going to just make it L over 2. But it's also not perpendicular to the lever arm, right?
Right.
So you need to get this component. And you could figure that out yourself, but it ends up being, I think it was sine 30. This angle here,
Where does oh right.
I gave this as 60. So you do some geometry. That's 30. Yeah, it ends up being sine 30. You can figure that out.
Okay.
And then plus the wall one. I not have any. Oh, wait, more space. Nice. Normal force from the wall. That one is a full L away, right?
Sure.
And that perpendicular component's actually sine 60. Again, you can figure that out.
Okay.
Because the perpendicular component is this one here. You see what I drew?
Yeah.
Poorly? Ends up being sine 60. All right, so here's where it comes in, where the question asks for the frictional force, but there's no friction in here, right?
Yeah.
But this is F wall. Let me make that clear. You see where we're going to get friction from?
Don't we? Wait. Not quite.
Look back up here.
It equals F wall.
Yeah, this is F wall. So you just plug that in.
Right.
So you plug this friction into here, and you solve for it, and you're done.
So what does the question actually ask for? Because I didn't read the question.
It asks for the frictional force is the first question. Yeah.
Oh, okay. So you would solve this thing down here for F wall, and then just that's F friction.
That's it. Yep.
Okay.
That's generally the hardest this will get.
Oh. All right.
Yeah. So definitely try that practice. Like, as usual, like if you're running out of time, maybe go straight to the hard ones. You know, you can skip some of the easy ones.
All right.
I don't want you wasting your time.
Yeah. Okay.
All right.
All right. Yeah, that helps. Also, do you could explain 32C on the intro to rotational things?
Sure. Let me get that up a second. Oh, right. That was a tricky one, too.
I understood it would slip. I was wondering what exactly happens and why.
Yeah. You know what? Let's just look at my... share. Can I just share this screen? means. All right. Do you see my screen?
Yes.
All right. I'm just going to go to our team files. And my answers to the introduction is here. All right. 32 over here, right?
Yeah, 32. Mostly C. I got
Okay.
A.
All right. So look what I did here. Fs max is mu SFN.
Sure.
And then, oh, okay. Here's the tricky part. So we haven't done this in class because it's accelerating in two directions. So I mean, it's one direction. It's accelerating, but there's two types of acceleration. There's
Sure.
changing your speed and changing your direction. So the tangential acceleration, this arrow here, I don't know. Can you see what I'm looking at? The
Yeah.
vector diagram. The tangential acceleration is changing the speed. The centripetal acceleration is changing the direction. You have a total acceleration that's diagonal.
Mm-hmm.
So you have both. So that acceleration, you have to take into account both things, both components.
Is there a reason you can't use any one particular acceleration?
That just doesn't give you the whole thing. I mean, that's only a part of it.
Okay.
It's not telling you the whole story.
And
The net force is giving a net acceleration.
All right.
The frictional force is doing both. That's the problem. If the frictional force was only contributing to one of those, then you'd be right. But the frictional force is the only horizontal force on this whole thing. So it has to be it has to be causing the entire acceleration, not just pieces of it.
Right.
So when I
Okay.
plug in for A, it has to be this whole square root of AC squared plus AT squared thing.
All right. And that gets that value.
Yeah.
So does it do anything like specific? Because I think it incorrect. I did something wrong, and I thought that it would slide towards the middle.
So I'm assuming no sliding, which makes me use static friction, right? Once you go past the max static, then you're going to slide.
Right. So I was wondering, like,
But,
if you pass that point, like, would it start moving so the radius changes to satisfy?
yeah, absolutely. The whole thing would get really freaking complicated.
Okay.
Yeah, your radius would change. All your accelerations would change.
Is there a reason that you chose that particular threshold where AC equals AT?
Oh, that's a good one too. Someone else asked me that. I didn't make this problem up. I think we did. It was there because it just makes it easier to solve. It just makes it like interesting in some way. It's not special.
Okay, but it's not like it's not like a special.
No, I should tell the whole class that too, because everybody seems to. Yeah, I can see why you would think that. It's not. It's not. It just happens. Like these two components that I drew down here. Whoops. Those two components are like happen to be equal. So who cares? I mean, like that's just it's a coincidence.
So it's just a coincidence that it starts slipping after those are no longer equal.
Yes, it's totally made up, arbitrary from the problem.
Okay.
Yeah. It's not a special thing.
All right. So another thing I was just kind of wondering. So because you find at that particular point that they give you that AC equals AT.
Yeah,
and what
that's
happens
given.
eventually is that AT doesn't change.
Why would
in this case AT is equal to alpha?
Not equal? Oh, because R is 1.
Yeah.
Sure, yeah.
And so that doesn't change, but W keeps changing, and so the AC is increasing.
Oh, weird.
Does that like cause a problem?
No, yeah, that's a good one, Dylan. You are a physicist. Yes, so that's why this is a very specific, like, first-year physics situation. Only at this very instant
All
would
right.
this happen. It has to be that exact instant where you're right. So if omega, no, wait a minute. Let me think about this for a second. So if omega is increasing, which it is, AC would increase, but alpha, I guess, is staying the same. Yeah, you're right. This is a very, very specific instant.
All right.
Yeah. This is not realistic. I mean, it's realistic. It's just not general.
Is it only specific because R is 1? Or something like
No,
that?
no. Even if it wasn't, R's staying constant. If the thing's not slipping, R's staying constant, so it wouldn't matter what R is.
All right.
You're absolutely right. It is a very specific situation that would change dramatically quickly,
Okay.
and you would get into a calculus-based problem.
And so in a problem like this, can we just say it slips, or do we have to, like, is there anything more that we have to say about that?
This asked what mu was
Well, for
At
for
the-
C.
for this particular point. Yeah. Oh, for C. Oh, yeah, it just slips. It's fine. You should probably say which direction it slips in.
What would happen to it? It would just kind of fly off in whatever direction it was going at the time?
Exactly. Yeah.
Okay.
It might actually, technically, it would probably be some sort of parabola because it's not like the force is zero. There'd probably still be kinetic friction. It would be weird. But yeah, the initial slippage would be whatever direction the tangential velocity was. You're right.
All right. So on a test, I could just put, slips, and that'd be fine.
Yeah. That's fine.
All right. All right, cool.
Thanks, man. That was great.
Yeah,
Hope that
thanks.
was helpful.
Oh, and sorry, one last thing.
Sure.
I've been uploading my things as just PDFs, or I think my first one was a JPEG, and then I uploaded a PDF. Is that like a problem? Was I supposed to do it a different way?
No, I think it's fine. Whoa, I just zoomed in. Hold on. Whoa, what is going on here? Let's see. I'll show you what I see. All right, what I see is, whoa, this is really zoomed in like I'm blind.
Oh, I saw. I accidentally modified that. That's my bad.
That's okay. So I look at grades. It's not actually showing grades. It's just showing what people turned in. And then I go to Dylan. And okay, so here, turned in. This is which one? Intro, motion. Open student work. You still see my screen, right?
Yeah.
Okay. Give it a second to load. It's slow. Unless it's not. Usually doesn't take this long.
Yeah, some of the stuff was taking a while today for me.
No, I'm just zoomed in way too much. I don't know why. Here, this is yours. Why am I, what the hell? I'm like zoomed in like crazy. Zoom out, please. Here we go. Zoom out.
That doesn't look like mine.
It's not?
That's not mine.
This is Milo. Okay. It's because it's all zoomed in. I don't know what's going on
Yeah.
here. Okay, let's go to yours, Dylan. All right, this one here, right?
Yes.
Okay. Okay. Again, here we go. Okay.
Yeah.
Again,
All right.
usually I don't get
You
those
got them
zoomed
in
in,
that order.
but I see them fine. Yeah.
Okay.
And then I
Is that okay
say,
to put them on loose leaf instead of?
I don't
on
care.
the-
Yeah, I can read it. Great
All
work.
Oh,
And
thanks.
the thing is, I could see how I could download it, so then I could print it out. I could do whatever I want.
All right.
Yeah,
Okay,
so you're
cool.
good. All right.
All right. Thank you.
Talking to you, Dylan. How do I stop this thing?